Ladies and gentlemen, welcome to the Geological Society of London and to this, the second Society London lecture in 2015 entitled When Continents Collide, Active Deformation and Seismic Hazard. My name is Ted Neild and I am the editor of Geoscientist. Free copies available on the mantelpiece outside. Please do help yourself. It's my pleasure today to introduce today's speaker, Professor Tim Wright of Leeds University. Since 1900, 35 earthquakes worldwide have each killed at least 10,000 people. Of these, 26 were in the Alpine-Himalayan seismic belt, along faults that had not previously been identified. During the long periods between events, the ground surface around seismic faults steadily warps in response to tectonic forces. In this lecture, we will hear how we can use the latest satellites to make extraordinarily accurate measurements of how continents deform, how we can use this information to understand where damaging earthquakes are likely to occur, and how the results can be used to reduce the devastating impacts of those earthquakes. Our speaker is Professor of Satellite Geodesy at Leeds and Director of the NERC Centre for the Observation and Modelling of Earthquakes, Volcanoes and Tectonics, conveniently known as COMET. His work has been at the forefront of developing the use of satellite radar for measuring tectonic and volcanic deformation. In 2006, he was awarded the Society's William Smith Fund and a Philip Leverhulme Prize. Last year, he won the AGU Geodesy Section Award, and later this year, he will deliver the Bullerwell Lecture of the British Geophysical Association. Ladies and gentlemen, please welcome Professor Tim Wright.
Well, thank you for that introduction, and thank you for all coming. It's a great pleasure to see such a full room. Before I begin, really I want to get my thanks out of the way at the start, and in particularly these people, most of whom are within COMET, this organisation that I run, and particularly John Elliott and Barry Parsons at Oxford, Laura Gregory and Richard Walters at Leeds, James Jackson at Cambridge, and then some external collaborators, Hua Wang and Corne Kramer. So you had, I think, a few minutes to digest this figure, which is a fairly sobering figure. It shows the earthquakes that have killed more than 10,000 people, the 35 earthquakes that Ted mentioned in the introduction. The size of the circle is proportional to the number of people who died. Most of those, so 75% of those earthquakes, have happened in this region called the Alpine-Himalayan belt, which is where the crust is being subjected to the collision of Africa, Arabia and India with the Eurasian plate. Now, the number of people who die in earthquakes is increasing, and we can quantify that in this, again, another sobering graph. In the Middle Ages, and we know really that the earthquakes that killed more than 10,000 people, we know pretty well. If that happens, somebody writes it down. It was roughly in the Middle Ages once every 20 years. Moved to once every 5 years between 1600 and 1900. In the 20th century, there was an earthquake that killed more than 10,000 people every 3.3 years. And this year, we've had this century so far, we've already had 7 of those events in the 15 years of this century so far, including some really devastating events that you've all seen on the news. The BAM earthquake is one particularly devastating event. It wiped out nearly half of the town of Bam in Iran. In the old town, this is part of the old town where buildings were made of these mud adobe bricks. Almost nobody was able to survive. Here's a satellite photo following the event. And if you look at this is actually a photograph after the event of the buildings having been reconstructed, but you get a sense of the amount of destruction that took place. In Pakistan, in 2005, another devastating event, again an aerial shot of a town along the fault rupture. The fault rupture is there. This is on the Himalayan thrust as India is colliding with Asia. If we want to actually do something about this, then really you need to think about assessing the hazard accurately. You need to think about what we do about mitigating the hazard, how we plan and engineer to do that. And we also need to think about economics and what are the cost benefits of doing that compared to spending money on other things, of course. In this talk, I really want to focus on the scientific part. What can we do in terms of hazard assessment? I'm kind of motivated and encouraged by the American experience. So in California, since the 1906 earthquake on the San Andreas fault, people have really known about the hazard, they've studied that hazard, and they've really characterized that hazard very well. And so when we have an earthquake like the magnitude 6 Napa earthquake that happened on the 24th of August 2014, this only resulted in one loss of life. And really, earthquakes in California are about economic losses now, and in this particular case, about the losses to the wine industry. So in the Napa Valley, it's a real tragedy, isn't it? But about $1 billion of damage to the Napa Valley wine industry. This was another one of my favorite photographs, again, from Twitter. This shows what Californians do with a fault rupture. So there's this new opportunity just here for skateboarding. So something can be done. We can build and we can create communities that are resilient to earthquakes. So here are my take-home messages. Actually, assessing seismic hazard is really hard. It's not an easy problem at all. And existing methods aren't working that well. They're failing in certain examples. And so I want to argue that satellites can really help us identify areas most at risk from earthquakes. And I want to talk at the end a bit about our role as scientists in terms of policy and influencing society to be able to become more resilient to earthquakes. So let's start with thinking about why this is a difficult problem. So here's a map. This shows the Alpine-Himalayan belt. We're starting at Italy there in the west, going through to Tibet and China in the east. And what you can see, these red dots are magnitude 6 earthquakes that have happened in the last 30 years or so. And what you can see is this plate boundary is not a narrow zone. This is not a thin line separating the African, the Arabian, and the Indian plates from the Eurasian plate. This is a broad zone. It's up to 2,000 kilometers or more in width. So this is not like a plate boundary in the oceans, where you've got one plate diving under another in a very narrow, very well-confined region. This is a broad area. The second problem is earthquakes are rare. So we can illustrate that very nicely by looking at different time periods. So since 1976, we've had very good locations and mechanisms for these earthquakes. We know a lot about earthquakes since 1976. This is all the magnitude 6 plus earthquakes in that time. We've got pretty good locations from seismic instruments for the bigger earthquakes, at least, back to about 1901, when we had enough seismometers to be able to start locating earthquakes. And this is the map of those, and you can see already that there are some quite significant regions, for example, up here, where there are earthquakes in between 1901 and 1975 in regions that had no seismicity in the recent record. If we go on, we can also have a fairly decent record back to of the very big earthquakes for something like 1,000 years, and it varies. The quality of this record varies from place to place, and of course is dependent on where people are living. So it's a rather biased sample. But again, you can see that in the historical record, there are earthquakes, for example, here in this region known as the Ordus block, where there were earthquakes in historical times where there hasn't been seismicity in recent times. Look at the Dead Sea Fault down here. So there's a number of regions where if we just looked at the recent record, we wouldn't be seeing the full picture. We can also look at this map, and on the black lines on this map are showing active faults, and you can see that there are some active faults, for example, here in Central Asia, that are mapped on here that haven't had earthquakes on them. So usually you have earthquakes on active faults, so perhaps even this historical record isn't long enough. And actually we don't know where all the faults are, and this is a major problem in continental tectonics. And we don't know where they are because actually they're pretty hard to find. So anyone spot the faults in there? It's a pretty subtle feature running through the landscape. So there you are, that will help you. So there's the fault. Finding these structures is a real skill, and it's something that scientists within COMET have developed, the ability to read satellite images and to go into the field and make these kind of observations. But it's a real challenging process, and it's time consuming and it's difficult. So I'm often envious of my colleagues who work on volcanoes. So in terms of the hazard problem, they offer several advantages. One is we know where most of them are. They're often sticking out like this. This is Mount St. Helens in the States. So we don't get so many hidden volcanoes. The second is they're point sources. So earthquake faults can be extended over hundreds of kilometers in many cases. And thirdly, actually, volcanoes will often have precursory activity. So earthquakes, we don't usually get any precursory activity. They happen without warning. Whereas volcanoes, the magma has to come from depth up to the surface. And so usually this provides some warning. It can be quite brief, but usually there's often an opportunity to evacuate. And I think this is a kind of sobering statistic in terms of the relative impacts on society of volcanoes and earthquakes. So 20 seconds of shaking in Haiti killed more people than all volcanic eruptions in recorded history. So that gives you a kind of perspective, and that's partly because earthquakes are more dangerous, but it also reflects, of course, the knowledge and the ability to warn people about impending volcanic eruptions. Okay, so it's a difficult problem. Let's look at how we try and deal with it and what the traditional methods have been for dealing with this problem. So the state of the art really out there is a technique called probabilistic seismic hazard analysis. And in that technique, basically what we're trying to do is work out the probabilities of any point on the Earth receiving strong shaking. And to make that kind of calculation, what you do is you take a seismic catalogue, and that could be an instrumental seismic catalogue over a relatively short time. It could include the historical records if they're available. You take whatever you can. So you take the history of past earthquakes, and then you use some equations that are schematically represented up there that relate you, if you're at a certain distance from an earthquake, how much shaking will you receive. And then you take each point on your map and you say, well, I'm going to receive a certain amount of shaking from all these earthquakes, and perhaps we use some geological knowledge as well and say there might be other types of earthquake in there. We might use some knowledge of faults. And you can come up with a map. But basically, these are governed really by where earthquakes happened in the past. Here's an example from 1999, a fairly old map now, but this was a global assessment of seismic hazard. And the red areas are areas with identified high seismic hazard. Let's just focus in on a couple of areas. So let's look at Mongolia to start with. Mongolia is just on that northern edge of the collision between India and Asia. This is actually a slightly more modern seismic hazard map of Mongolia, one produced by the UN in 2010. What you can see again is these red regions that show areas of high seismic hazard. There's these three regions just there. If we just focus in on that region and compare it to some other data, so this map is a rather complex map, but focus to start with on these red beach balls. So these red beach ball patterns here are where three big earthquakes happened in 1931, 1905, and 1957. And if you look on those seismic hazard maps, those three areas of high seismic hazard on the hazard map basically correspond to those regions of where those previous earthquakes happened. Now, also shown on this map is information about active faults. So you can see on here, these lines are all showing mapped active faults that's been done with this painstaking work looking at satellite imagery going into the field. And you can see this region here has faults that basically are just as prominent on the ground as the faults that failed in those recent earthquakes. And if we translate that onto the hazard map, you can see there are parts of the region that are identified as having low hazard, but actually have major active faults in them. So the hazard in those regions, geologically, I don't think is any different. In fact, it might well be higher than the places that had the earthquakes, because these will be places that are overdue perhaps for failure. So really the message here is that records of earthquakes are too short. So these faults in Mongolia might fail once every 10,000 years. So even if we've got a really good historical record for 1,000 years, then it's not going to be enough in somewhere like Mongolia. So this conventional approach isn't working. We can also illustrate that in Haiti. So if we focus in on Haiti, now before the 2010 earthquake, then that global seismic hazard map really was the best hazard map available for Haiti. This is the hazard map, and again, the red colours are high hazard, the yellow colours are relatively low hazard. And what you can see is the earthquake happened just here, where that star is in that region that have been identified as low seismic hazard. So what is the conventional approach? This happens, our seismic hazard map is wrong, well, we just make a new seismic hazard map, right? So here's the seismic hazard map after the Haiti earthquake, and lo and behold, the area that had the earthquake has a very strong high hazard. Is there anyone from Texas in the audience? Okay, so statisticians know this effect as Texas sharpshooting, right? Okay, so this is how it works. So we draw our hazard map. Okay, so there's our target, right? And then we have our earthquake. We shoot our gun in this case. There we go. I spent hours on this in PowerPoint. Okay, so we miss our target. Oh, and so okay, so Texas sharpshooting is this. Well, we just get rid of the target and we redraw the target where it was. Okay, so this happens in seismic hazard analysis, and it's a problem because actually we'd like to be able to say something about where the future earthquakes will take place, not where the previous ones have been. And I also like this quote from Hiro Kanemori, which is, it's hard to predict earthquakes, especially before they happen. Right, so. Okay, so existing seismic hazard methods aren't working that well. I want to spend some time now talking about satellite methods and what we're trying to do to improve the situation. So I want to argue that satellite methods can identify areas at risk, and to do that we need to go back and think about what causes earthquakes. And so here's a cartoon, and this idea really was developed way back after the San Francisco earthquake, based on very careful observations that were made at the time. So this is a map, a schematic map of a block of crust either side of a tectonic fault. That fault, that region is about 100 kilometers wide, and in this case we're shearing across the fault. And this process takes a long time. So we might be 10,000 years for some faults in Mongolia. It might be 30, 40 years for some other faults that happen more quickly. But as we shear, we distort and build up elastic energy in that crust. It's like basically pulling on an elastic band almost. We're basically building up elastic energy based on those far field plate motions. Then the earthquake happens. So the earthquake happens very, very quickly, typically in tens of seconds for magnitude 6 earthquakes, up to a minute or two for the very largest of earthquakes. And in that time, the elastic energy is all released. These two blocks kind of spring back. Most of that energy is radiated much of that energy is radiated as seismic waves, and we get this displacement at the fault. So the idea, and what I want to try and convince you of, is if we can actually map this warping that's happening between earthquakes. It's small and it's subtle. We're talking about millimeters per year over distances of 100 kilometers. So these are very small motions. But if we can measure it, it should be able to tell us something about where earthquakes will occur and how often. So let's test that idea with modern data. I think one of the best tests is from data in California. So this is California. The red zone along the edge here is the San Andreas fault system. This is the Great Valley here, and going into the Sierras and the Basin and Range across the Wasatch Fault here. And what we've done, what's been done actually by Corne Kramer at the University of Reno here, is he's taken all the measurements of surface displacements in this region and calculated how much the crust is straining. And the red colours are areas of high strain, and the blue areas are places where there's low strain. And we can compare that then to maps of where the earthquakes actually take place. And I think this is a rather remarkable agreement when you look at this map on the left, which is a measure of the amount of earthquake activity. The details, again, of what was actually being shown don't matter, but the red colours, again, are high activity, and the blue areas are low activity. So again, you've got these main features. You've got high seismicity along the San Andreas system, into the Sierras and Western Basin and Range, and also along the Wasatch Fault there. So we've got very good agreement between this geodetic observation of strain and where earthquakes have taken place. Okay, well, that's fine, but maybe that's just saying something about, well, maybe the earthquakes are just releasing that strain, and we're not, is it a correlation or a causation? We have to be very careful about these things. So another thing we can do is actually look at a completely independent data set again, and look at how fast faults are slipping. And we can measure that geologically by looking for features that are offset across the faults. If we can work out how old those features are, measure the amount of offset, we can actually work out a slip rate for the faults. And these are average slip rates, typically over 10,000 years, 100,000 years, sometimes longer with geological offsets. So we can get a noisy estimate, but an estimate of the slip rate from these geological methods. We can do the same thing with the geodesy. We can build models that look at this warping and see how much slip rate we would need on individual faults to measure that warping, and then we can compare those two observations. And what we can see is there's some scatter, but actually there's a pretty good agreement between the rates we get from these geodesic observations, which are made over quite a short period of time, so typically maybe over a decade, compared to the geological slip rates, which are measured over 10,000 years. So the geodesy really does seem to be saying something about the long-term rates on these faults that's useful. We can also compare the strain rate, and in this case we're comparing strain rate from a low resolution model to actually where people die in earthquakes. And this is a rather, again, one of these sobering figures, and I'll keep introducing these, I'm afraid, throughout the talk. But it's a rather complex figure, but this is a cumulative histogram. So basically what you need to know is that to the right of that point, we've got 96% of all the people who die in earthquakes, and 96% of all earthquake deaths are in regions with strain rates greater than 1 millimeter per year over 100 kilometers. And 77% of people who die in earthquakes, the region that they're living in is straining at less than 5 millimeters per year. So this is telling us that strain is important, so that basically if we can measure strain, we can say something about the majority of earthquakes. And it's also saying that actually we need to be very, very accurate in these determinations. So being able to measure a millimeter per year over 100 kilometers is pretty challenging. So how do we do it? So there's a couple of ways that this is done. One is using GPS receivers. So many of you will have GPS in your car or in your phone, and you're kind of used to that giving you a reasonably accurate position, enough to be able to navigate with most of the time when you can see the satellites. But what we can do with these instruments is actually track the satellites over much longer periods of time and actually pin these points down to about a millimeter in terms of their absolute position. So instead of the 10 meters or so you can get in your car, by actually tracking the signals, we can be much more accurate. And we do this in two ways. So on the left, what's happening here, these are two sites in Ethiopia. So I do a lot of field work in Ethiopia. We're trying to measure the rifting there, and so these sites, typically we've trekked for several days with all this kit on the back of camels to try and get to these sites. It's a lot of fun. That one on the left, basically we drill a pin into the rock, we measure just for a few days where that pin is, then we come back at a later time and remeasure it. So that would be sort of campaign style GPS. And in this one, we actually leave the receiver in the ground, and we come back to it later on and download the data. And there are many of these continuously recording stations all over the world now that are streaming data over the internet. We can't do that in Ethiopia, but we can do that in many parts of the world. So there's a huge amount of data out there. And we can see that by looking at the sites in the world where there are GPS stations. And so each of these dots is a site with GPS stations, and the blue ones are streaming data back to the University of Reno all the time. If we zoom in on Tibet, you can see there's a pretty good distribution of those sites. The numbers involved, so we've got something like 17,500 stations now involved in making these measurements, compared to a decade ago when we had about 4,000. So really, it's really exploding at the moment because these instruments are getting cheaper, more and more people know how to make these measurements, and they're becoming more and more important in many other areas of society as well. We can get these observations. And this is what those displacements look like. I think it's a rather beautiful pattern that shows the influence of those colliding continents. So remember, we've got Africa coming up here, we've got Arabia that way, and India even stronger there. And you can see again the influence of those collisions and how it's extended over quite a broad region. So there's the Himalayan front, but we've got displacements from that all the way out here beyond Mongolia, actually. So we're really influencing a huge region, and we can see rather beautiful things. We can see these GPS displacements kind of being diverted around, and we think that's due to the topography of Tibet flowing around the corner. We can see the similar thing happening in Turkey as points move around there. So there's a huge amount of information in these kind of data sets. What we can do with it, one thing we can do with it is turn them into strain measurements. So we can take those and we can try and calculate, based on all these observations, how much the crust is straining, how much of deformation are we getting. And that's what's shown in this figure. This is a strain map derived from those GPS data. And you can see it has some really nice features. So it has, you can see the Himalayan front very clearly, and it's clear an area where we've got high strains. And you can see some individual fault structures coming out here quite clearly in the data. In Turkey as well, we've got some areas of very high strain. So it's a very powerful new tool. You can also see it's a little bit patchy, right? So we've got areas like here where it's just looks a little bit noisy. And so do we believe all of the features in this? Well, no. And if we, we'll come back to that actually. So let's assume we do believe all those features to start with. We can turn those strains into a forecast of seismicity rate. It's a rather low resolution one. It's not a really high resolution one. And this is a global model, but this is work done by Bird and Creamer and just published last year. And again, the colors represent the amount of earthquakes we might expect to take place. So this is a prediction now of seismicity into the future, rather than being based on what earthquakes have happened in the past. The green, just that they present these things in a rather interesting color scale. So we've got log 10 of epicentroids per meter squared per second, which most people don't think in those units, right? So the green color is one earthquake per century in a region 100 by 100 kilometers wide. And then if we went to this kind of yellowy orange color, we'd be at 10 earthquakes in that region. So that's the kind of scale we're talking about. And here's where the earthquakes actually happen. So then this is earthquakes that weren't used to constrain this model. So these were earthquakes happening between 2005 and 2012. And you can see what happens is they match rather nicely that distribution of strain, at least in its broader sense. You can see there are a few exceptions, right? So we do get earthquakes outside these zones. And actually, in terms of the details, this isn't enough to actually say this model's right or not, because we can also do quite well with historical seismicity over similar time periods. But so the GPS model is fantastic, and it's really getting better all the time. But those GPS observations are still relatively sparse. So that kind of bobbly noise you saw in the GPS model comes from the fact that we haven't got a really nice dense grid. What you really want is one of these measurements every 10 kilometers or so on the ground, really measuring exactly where you are and how all those points are moving. And really the only place on the planet where we've got that is Japan. And Japan does have a very dense network of systematically laid out GPS receivers. But most parts of the world, it's much, much sparser. And particularly when you get into regions like the India-Asia collision, we've got large gaps here in the data where we've got no observations at all. Much of India has no observations at all. Even where the stations are relatively dense out here in China, then actually the station space in there is still about 50 kilometers. And remember, we're thinking about points here that are straining over length scales of 100 kilometers. So if we actually want to identify where that strain is coming from, we really do need a denser set of observations. So how can we do that? Well, really, my scientific career has actually been involved in using and developing satellite radars to try and do this. And I've been doing this for 15 years or so now. And this is the latest satellite we've got. It's a satellite from the European Space Agency, a rather beautiful satellite called Sentinel-1. It's a radar satellite. It's sending radar energy down to the ground surface, records the reflections. And what you'll see in this next slide is that radar acquisition taking place. This was one just after Sentinel reached its final orbit on the 7th of August 2014. Came back 24 days later, took another image, And this is the clever bit. So what you can do is you can combine those images very precisely, and you can get these colourful maps, and these are called interferograms. And these give us precise measurements of how the ground moves between those two data sets. If you can see in here, what you can see is these coloured fringe patterns. And you can basically treat these as contours of the surface deformation. And the contours have a contour interval of about 3 centimetres in this case. So what we've got here is about 10 centimetres of deformation between here and here. You can see it's quite noisy as well, and the main source of the noise in here is the atmosphere. So a single interferogram measured in this way between 2 radar images isn't going to be accurate enough to get that 1 millimetre per year over 100 kilometres. What you need to do to get that is take a whole stack of images acquired over as long a period as you can, so over 10 years, 20 years actually with some satellite systems, some of the European satellite systems, we can take 20-year stacks of data. And then you can look at individual pixels and see how they change through time, and you can build up these kind of maps that we see on the right. And those do have an accuracy that's approaching 1 millimetre per year. In this particular case, you can see that change in colour from red to the north of this fault here and green to the south of the fault. And that's consistent with this shear across the fault. And you can see that shear is happening in quite a narrow region. That region's on the order of 20 kilometres or so. Here's another example, and particularly this is an example from eastern Turkey where we've actually used those INSAR observations to map strain. So if you remember, in Turkey we've got Arabia travelling north, and what's happening here is it's squeezing Turkey out to the side. It's a bit like a pip caught in that collision. And if we look at data in that region, there's a lot of radar data acquired in that region. It's also a region where we have very good GPS observations. It's a very good region for testing these kind of ideas. So we can map strain, and we can map strain. This is the solution from GPS only. And again, the red areas show the areas of high strain, and they're mostly along these 2 faults here, the North Anatolian Fault in the north and the East Anatolian Fault in the south. We can do exactly the same thing with just the radar data from the INSAR, and this is what we get. The INSAR data is particularly well constrained within that region there. Outside that region, there's some observations, but they're not as good. And so what you can see is, again, we see very clearly we can map the strain here in eastern Turkey from just the satellite observations. So I think this has been some things we've been working towards for as I say, for 15 years or so, and we're particularly pleased we can do this. It's an area where the slip rates are quite high, and actually to be able to do this in other regions is more challenging, because the slip rate on the North Anatolian Fault is 20 millimetres per year, and on the East Anatolian Fault is 10 millimetres per year. And with the data from existing satellites, that's approaching the limit. So we think we can get down to about 5 millimetres per year with existing satellites. But with the Sentinel-1 system that was launched last year, we're going to be able to do much better, and we'll be able to do it much quicker. So this satellite is funded by the EU. So this is your EU tax pounds going into funding this system. It actually has a huge number of purposes, but one of them will be for making these kinds of measurements systematically over tectonic belts. So what we're doing is we're acquiring images every 12 days with one satellite, and a second satellite will be launched next year, so there'll be a pair of these satellites. And this mission is funded for 20 years. So we're going to have a sequence of these satellites continually launched, acquiring data every time the satellite goes over these tectonic belts. A really boring data set and a really boring satellite. I mean, satellite engineers like to build these very complicated satellites where you can change the mode and point in different directions and change the resolutions. But that really messes up this technique. What we need is the same kind of data again and again and again every time it goes over. And with these satellites, we're going to be getting huge volumes of data. And what we're doing within COMET is trying to build a system that's processing all of that data. So we think we get about 0.5 terabyte a day. So it's going to fill up your desktop computer pretty quickly, right? So we've got some major computational facilities that we're using to process those data. And the aim is within about 3 years to have a much higher resolution global strain rate map. Because the data are being acquired so frequently, you can get there much quicker than we've been able to do with data in the archive. So watch the space for that. So we think 3 years, 3 to 5 years, I'd say, to give myself a bit more wriggle room. We should have this high resolution map of global tectonic strain. Actually, that's still not enough, really, because there are those regions that have an earthquake once every 10,000 years. And if you have a meter of slip every 10,000 years, I've now set myself up to doing mental arithmetic, which I'm not going to do, but it's less than a millimeter per year. It's 0.1 or 0.01 anyway. But a very small slit rates beyond what we're going to be able to do in the next few years with geodesy anyway. So these satellite techniques that I talked about earlier for looking at the landscape really come into their own for these very, very slow slipping rates. And again, the challenge here is can you identify where the faults take place? It's pretty tough. Perhaps this bottom right image, which is the zoom of the zoom, it's maybe more straightforward. You can see those features running through the landscape there, perhaps in this one through there. But in here, they kind of run through like that. All I'll do is just remove those and then put the proper interpreted lines on. But these are subtle features, and actually the people who do this, like Laura, who's now in Leeds, they spend hours and hours poring over these high resolution images on Google Earth, downloading extra high resolution data from different satellites, identifying these features, and then targeting particular sites to go and visit in the field. And again, this is a fault rupture again in Mongolia. This slip rate, this has had an earthquake, probably a magnitude 7 earthquake on it at some time in the last 1,000 years. We have no idea when, but it's clearly there, and it's in an area that's mapped as low seismic hazard. So we need to integrate the satellite geodesy methods with these other satellite methods that are designed for observing optical features. Okay, so I'm going to start to wrap up. I'm going to think and leave plenty of time for questions. So let's try and think about the next step, and let's think about influencing policy and influencing society to try and do something about this, to try and at least slow down that rate of increase in the number of people who are dying in earthquakes. So I've talked about the science. The question is, how do we get the science into the policy? And that's challenging. And that's really but that there are perhaps as many as 316,000 people who died in this earthquake. Now, 2 years before that earthquake, and remember this is an area that's mapped as low seismic hazard on that global seismic hazard map, but 2 years before that earthquake, this was published by Manaka, Calais and others. So the Enriquillo fault, which is the one that caused the earthquake in Haiti, is currently capable of a magnitude 7.2 earthquake if the entire elastic strain accumulated since the last major earthquake was released in a single event today. So the knowledge was there in the scientific literature, but of course that's not good enough. Actually, we need to do more. So the question is, how do you make sure that decision makers and citizens as well are well informed about that hazard and can make informed decisions about whether we should invest in a retrofitting campaign or not. And a project that I'm very proud to be involved with is one called Earthquakes Without Frontiers. That's an innovative project funded by the National Environment Research Council and the Economic and Social Research Council. And really, it's a collaboration between physical scientists and social scientists and also practitioners. And we're working with the Overseas Development Institute. And the idea is to try and share knowledge, kind of the really up-to-date knowledge about what the hazard is with people who actually know how to influence people and how to make changes. And we've been going a couple of years now, and this is some of the challenges involved in that social scientists speak completely different languages to what we speak as physical scientists. You know, we can't put equations up, they run, that's an exaggeration actually, some of them can do equations, I'm being, but we're learning to communicate amongst ourselves. But we're also involved in a huge number of partners, and I think the really exciting thing here is this partnership, and this partnership is built across the Alpine-Himalayan belt between universities, working in physical sciences, working in social sciences, teams from geological surveys and other decision makers. And of course, there are links between the UK and all of those, but actually the really important ones are these. So it's the fact that Chinese scientists can talk to Italian scientists about normal faults. They both have normal faults, which are extensional features, very similar geology, and they can talk to each other about their experiences. The Iranians and the Indians can talk about thrust faulting. The Turkey and in Turkey and Kazakhstan, the scientists and decision makers can get together and think about how to deal with these big strike slip faults. And actually all sorts of other connections are going on there, things that we haven't planned. So I think it's that's the really important thing about this project, is bringing people together so we're learning from each other's experiences, and we can actually say, well, when something has gone wrong, let's try and do better next time. And the project really is kind of coming at this problem from two different ends. So it's coming at it from the top down, so thinking about trying to influence policy makers. So this is from a meeting we had in China, and it's also coming at it from the bottom up. So this is in Nepal, they have an earthquake safety day, which is fantastic. And so this is some of the EWF team actually out there on the holding the banners on this earthquake information day. So I want to end by with this picture of Nick Ambraces and a couple of quotes from him. So he was a really incredible scientist that worked at Imperial College, and much of those historical records of earthquakes come from Nick. And he coined this phrase that earthquakes don't kill people, buildings do. Let's take that a bit further. He also said that the collapse of buildings and earthquakes are not acts of God, and they're all too often nowadays are acts of criminal negligence. Now, I think in what we want to do is kind of move actually even beyond that, and then think about who allowed these buildings to be built. You can't necessarily blame the engineers for building things. And this is a school in Sichuan that was built right on the future rupture of the Wenchuan earthquake, the earthquake that killed 80,000 people. Again, you can see the fault rupture running through there. This school didn't collapse, but very lucky escape, I think, given where the fault came up at the surface. This is a photograph I took last year in Leh, in Ladakh, and actually the buildings here, this is an area that hasn't had an earthquake for a long time, but I think is potentially at risk of earthquakes. And buildings are built like this throughout the Alpine-Himalayan belt with these mud bricks, and as soon as there's any shaking at all, these buildings collapse. So what are decisions being made with the correct scientific information or not? And I want to end on something slightly more positive. So here's a picture of one of my favourite places in the world, which is Istanbul. And you will all remember the 1999 earthquakes that killed about 30,000 people on the North Anatolian Fault in Turkey. And Istanbul is a very famous seismic gap. It's an area that hasn't had an earthquake for a couple of 100 years. And the Turkish authorities have recognised this now, and there's a major effort in retrofitting buildings, schools, hospitals, infrastructure. So if you recognise the hazard, things can be done, and you have to have the political will to do it, of course, but things can be done. So I will leave it there. Thank you very much.
Well, thank you very much, Tim. We have a quarter of an hour for questions. So I'll do what I usually do. I'll take questions from this block, then this block, then this block, and I'll try and spread it out over the quarter of an hour that we have for questions. Nick has to go off and do a podcast at 4 o'clock because we work our speakers very hard here. So if I can call you for a question, could you wait until the microphone is in your hand, please? It's not for our benefit; it's for the benefit of the millions of people who are listening online.
Yes, hello everybody. Yeah,
thanks for the lovely lecture. The growth in numbers of people killed is surely a function of the hockey stick growth of the population in the world,
Yeah,
and of people moving and living where they never lived before.
absolutely, yeah. And that's the more and more people are living in, and I should have said that at the time of the slide, more and more people are living in these megacities as well. And many of those megacities are located on active fault zones. And there are some good reasons for that. Actually, active fault zones make nice mountains. They can make water resources. They can make places that are pleasant to live in otherwise inhospitable areas. But yes, indeed, this growth in population has led to that explosion in the number of people who are dying. But actually, it's carrying on growing, and the population's due to expand by another 2 or 3 billion over the next few decades. And so, wouldn't it be great if we could stop that growth and say, let's build those 3 billion new homes safely, and not, and particularly the ones obviously in the areas at risk.
I was just thinking that have you discovered new faults? Because I remember once reading about that the Washington Monument was damaged by an earthquake, and they didn't even know that any faults in that area.
Yeah, so I think some of the new faults. So actually, many earthquakes have happened over the last 20 years on faults that we didn't know about. So actually, even in California, that Napa Valley earthquake happened near a fault that we knew about. And some of it ruptured bits of faults we knew about, but actually it ruptured some brand new faults that we had no idea were there at the same time. So we found faults. It's very easy after the earthquake to find the fault, but actually even that can be challenging in somewhere like Iran. The BAM earthquake, it wasn't until we had the satellite data that we identified the faults. Identifying them directly from the INSAR and those strain observations has been more challenging. What we've tended to do so far is try and prove that this works by looking at the faults that we know about. So the next challenge of doing this systematic global processing is to then look for the things we don't know about. The ones where we've had a lot of success within COMET of identifying unknown faults is by looking at these geomorphological features, by looking at the high resolution optical imagery, the high resolution topography, looking for those really subtle features in the landscape. And there's a whole host of faults that have been discovered there because of this work that we had no idea about beforehand.
If I understood some of your diagrams correctly, you identified areas of both high positive strain and negative strain. Is there any particular significance of areas of high negative strain?
Yes, so sometimes there are places within these collision belts that don't have a lot of deformation, and they're identified as these areas of low strain, and they should be areas that are relatively safe. So the reason for those, we think, is that you've got areas that are just a bit stronger. So, for example, within California, we think that the basin area just to the east of the San Andreas, so the Great Valley just to the east of the San Andreas fault, we think is a block of relatively strong crust, and so it's harder to deform that region, and so you get the earthquakes around the edges of those blocks. The same in Tarim Basin in Tibet, you've got some regions there that we think are stronger. So yes, there are definitely variations. It's not a systematic, uniform distribution of strain. Okay.
Thank you. Well, moving on to the middle block, I wonder if there's anybody here.
Have you any thoughts about how this accumulating information can be passed on to the general public and so on without causing alarm and good order and so on?
It's challenging. It's one of the things we're thinking about with the Earthquakes Without Frontiers problem. I mean, one of the particular focus areas there is in Nepal and Kathmandu. There will be a very large earthquake in Kathmandu at some point in the near future. And there, it is about educating people. It's also about doing things, and so there are a whole bunch of community programs that are involved, and this is local organisation that's very good at Nepal earthquake. Yeah, I can't remember the exact acronym. NSET is what they're called. But they're very good at arranging these programs, working with school kids, doing these campaign days. Whether you can do it without scaring people, maybe people do need to be scared. The big tsunami earthquake in 2004, of course, killed 250,000 people or so. When we had the earthquake in Japan, by the time we had the earthquake in Japan, we knew a lot more about tsunamis. At that point, people knew more about tsunamis, and there's a tenth of the deaths in that particular one. It was still a major disaster, of course. But so I think people know about some of these hazards more, but I think actually scaring people can perhaps be effective. You know, when these events happen, these are teachable moments, if you like. And so the USGS, if there's a small earthquake somewhere, they'll have somebody on that local news saying, well, this is what you need to do to get ready for the big one. You need to make sure your shelves are screwed to the walls. And yeah, the lady who died in the Napa Valley earthquake was because the TV set fell off and hit her. So it was entirely preventable. Yes, television is clearly bad for you.
You just mentioned the tsunami that hit Japan.
Yeah.
I believe that was caused by a seafloor earthquake.
Yes.
Do you take account of seafloor earthquakes?
Yeah. Yeah, so I deliberately kind of focus mostly on the continental earthquakes rather than these seafloor earthquakes where one plate goes under another. So part of the reason for that is that more people die in those continental earthquakes actually than in the seafloor earthquakes. And the seafloor earthquakes are a little bit more straightforward in that we know at least where the big faults are. So the challenge in those seafloor earthquakes is actually working out how big those earthquakes are going to be. And the big failing in Japan was that people thought we were going to have a magnitude 8 earthquake, was the biggest you could get, and actually there's a magnitude 9. Actually, I've got a nice, let me show you this. So this is for those of you who might be want to know about earthquake magnitudes. So this is a good analogy, I think, involving sticks of spaghetti. So a magnitude 5 earthquake would be like breaking one stick of spaghetti. So that's about the biggest we get in the UK. Very, very occasionally we get a magnitude 6 in the UK. There hasn't been one for about 80 years or so. So some of you remember the biggest one we have recently was a 5.2 in Market Raisin a few years back. So magnitude 6, and each time we go up 1 point on this magnitude scale, there's 30 times more energy. If we go up to magnitude 7, then we've got another 30 times. So we've now got 900 noodles, right? So you can feel already that's going to release a lot more energy when you break. Magnitude 8 is 27,000 noodles, and of course, there's your magnitude 9 earthquake, okay? So that's what happened in Japan. The problem was they were prepared for 27,000 noodles, and they got 810,000 noodles. So that's what went wrong there. But those seafloor earthquakes really do affect, of course, the regions around the coast are all being warped because of that motion and seafloors, and we can do exactly the same kinds of techniques to try and measure the warping near those subduction zones and to try and say something about the hazard on those offshore faults as well, yes. So that was a long answer to your question. I wanted to get the noodle analogy in. So.
Anybody else have a question from this? Yes, gentleman at the back and then later.
Hello. Is there any evidence that there's a sudden increase in deformation of the landscape just before a cataclysmic earthquake like in Haiti? And then do you envisage that your satellites could give future or precise information of the likelihood of an earthquake taking place?
So the short answer is no, unfortunately. So we really wanted that to be the case, and we've looked very, very carefully in many places. So there's a very famous experiment set up by the USGS, a place called Parkfield, where they'd had earthquakes every 30 years or so. There's various stories about that where the USGS made a prediction, and actually it was very, very late, the earthquake compared to their prediction. So it was a failed prediction, but they kept the instruments out there, and they did eventually record the displacements. They listened to all the seismometers. They were measuring gas, everything that you can imagine. Absolutely no precursors whatsoever. There's a hint, there's some very interesting papers and intriguing papers just been published on the Japan earthquake. And there they've got this fantastic GPS network that's been out there for 20 years in Japan. And they didn't see any short-term precursors, although there were some quite big foreshocks. So sometimes you get these earthquakes that in retrospect you know are foreshocks. Of course, you don't know they're a foreshock when you get a magnitude 7 earthquake. So distinguishing a foreshock looks like a regular earthquake. There's nothing special about it. But the interesting observation there is that the first 10 years before the earthquake, the velocities measured there are different from the preceding 10 years. So there is perhaps a long-term transient there that was observed in Japan, and that change is biggest in the area where the future earthquake happened. So there's a tentative hint that there's something in those data, but it would be more of a 10-year anomaly rather than a 10-hour anomaly or a 10-day anomaly.
Thank you very much. Years and years ago, there used to be there was a theory that you could sometimes lubricate a fault so it slipped before it got to the big one. Is there any currency in that nowadays?
Well, there are some faults that appear to be more lubricated. They kind of creep slowly, release the energy continuously rather than slowly. Rather than catastrophically in a big earthquake. But actually doing that in practice, I think, would be very challenging. And you can imagine the litigation if it goes wrong, right? If you're pumping lubricating fluid, first of all, you've got to get it down there, and actually drilling deep in the earth is very challenging. And probably the critical area is between 10 and 15 kilometers below the surface where these things nucleate. So it'd be challenging to get the fluid down there, but actually then you do it, and instead of it gently releasing, you get a magnitude 8 earthquake. Then yeah, I think it will be a high risk strategy. Yes.
Right, moving swiftly along. A gentleman on the back row to that.
I believe something called aftershock is responsible for as much damage as the original. So what are aftershocks and why do they happen?
Okay, good question. So aftershocks they tend to be smaller than the main shock. They happen because you break the main fault, but the faults aren't kind of perfectly straight. They're kind of irregular, and you get little bits that just need to adjust after you've had that big earthquake. So all these kind of blocks kind of jostling. You're also influencing the stress around the region. So if you imagine, can I tear this? Sorry, okay. So this is better way. So right, there's our fault, right? Okay. So you can see that tip there is ready to go. So right, so actually you know there's going to be a stress concentration at the tip of that fault. So you can actually calculate from an earthquake where the areas where there's elevated stress, and you can actually say something about the distribution of the aftershocks. So actually the aftershocks are one of the things we can predict much better than we can the main shocks. They can be as big as the main shock and as damaging. Usually they're an order of magnitude smaller. So if you have a 9, then the biggest aftershock would be an 8, and so on. But there's scatter and there's noise in that.
Just a quick comment to start with. I went to a lecture in Kathmandu about 40 years ago by a local engineer to an engineering society about construction of small buildings safely. Putting reinforcement in the right places. Yeah. And on another comment that somebody made about lubrication, it does appear that building large reservoirs sometimes effectively does that lubrication. I mean, you get earthquakes, inverted commas, caused by the reservoir, but in fact they're releasing it a bit earlier probably than it would have occurred because of higher water pressures in the fault. My question was going to be, are you able to take, your discussion seemed to suggest you're taking measurements of horizontal movement. Are you taking the same accuracy in vertical movements?
Yeah, no, in fact, so the GPS receivers are slightly less accurate in the vertical than they are in the horizontal. They're 2 or 3 times worse. So the GPS receivers we can do now a bit better than a millimetre per year with horizontal, and maybe 2 or 3 in the vertical. With the satellite radar, it's actually the other way around. They're looking quite steeply down, and we can measure more accurately in the vertical. So one of the nice things again about having the new satellite system is we'll be able to get the first kind of really accurate map of vertical motions, and we have no idea what we're going to see there in terms of the broad scale signals anyway. So that's quite yeah. Yes, yeah. And we can certainly use these exactly same techniques as well for looking at local scale deformation. So you could look at London, and there's very nice work being done where you can see when they were tunneling the Jubilee Line extension, for example, you can see the buildings above it sinking down. So you can use the same techniques for these much more local scale phenomena as well.
Many years ago, the Indian scientists told and had written in different papers that the tectonic plates, the large tectonic plates of India, moving 1.5 meter every year northward. If it is true, what is the cause? Why is moving frequently aftermath of frequently earthquake?
Yeah. So India, we now know we can measure it very accurately. The center of the Indian plate is moving at about 4 or 5 centimeters to the north in towards Asia, and we think the causes of that motion are basically mostly to do with convection in the Earth's mantle. So the Earth is kind of this big churning system. The plates, you have forces on the edges of the plates where they're being pushed, we have forces where they're being pulled, and we also have forces on the bottom of the plates due to this churning. So a mixture of those things causes these motions. Near where they're stuck, so India's ploughing northwards, but actually at the Himalayan front it's stuck, and there, if you were just to measure a very small distance across the fault, you wouldn't measure anything for most of the time, and then during the earthquakes you'll get 4 or 5, maybe 10 meters of motion that happens in a minute. So you can get very large motions locally that are releasing this slow motion that's built up steadily. Sorry, I missed that. Yes, no, this is moving continuously, yes. So, but at the fault itself, they mostly move only when there's the big earthquakes. Okay.
The hour of the podcast has come. So I wonder if you would remain seated briefly while I escort our speaker, and you can thank him in the usual way. Thank you very much. Thank you. Thank you.